All right, so now I want to show how we can use the Euclidean algorithm to solve congruences, like solve one congruence, and then we're going to look to see how we can solve systems of congruences. But of course, we need to know how to solve one congruence before we solve other congruences. So let's say we want to look at this equation. AX is equal, let's say AX is equal to B mod M. Now, the first thing, one of the things that we need to assume here is for there to be a solution, for us to be guaranteed that there is a solution, the GCD of A and M have to be equal to 1. So the GCD of A and M has to be equal to 1. If we want to guarantee the existence of a solution to this equation for whatever B we put here, the GCD of A and M have to be 1. Now, more generally, B needs to be a multiple of the GCD of A and M. So more generally, B needs to be a multiple of the GCD of A and M. That'd be explaining why that is would be another good thing to do in the discussion post. Anyways, so we're going to be assuming throughout that the GCD of A and M is equal to 1. Okay, so what we're going to do first, instead of solving this first, what we're going to do first is we're going to solve the congruence AX is equal to 1 mod M. So we're going to solve that AX is equal to 1 mod M. And then what we can do is if I want to solve this, if I multiply both sides of this equation, assume I find a solution, if I multiply both sides of this equation by B, it's going to read ABX is equal to B mod M. Okay, now what this says is that if we have a congruence like this and we multiply both sides of the congruence by a number, then we get the same congruence. So in other words, if the remainder that you get from AX after you divide by M is equal to 1, then the remainder that you get after dividing ABX by M is going to be equal to B. Okay, so I want to explain why this is true, and I want to explain it in a little more generality. So what this is saying, we're using the following fact, that if A is equal to B mod M, okay, so again, what this means is if you divide A by M and you divide B by M, the remainders are going to be the same. That's what it means for A and B to be equivalent modulo M. If you divide A by M or if you divide B by M, you're going to get the same remainder. Okay, so if this is true, what my claim is that if I multiply this equation by any number, by any integer, let's say K, Ka is going to be equal to Kb mod M. Okay, again, my claim is that Ka is going to be equal to Kb mod M. Now, I'm not saying that the remainder of Ka after you divide by M is the same as the remainder when you divide A by M, but I'm saying the remainder of Ka when you divide by M is the same as the remainder of Kb when you divide by M. Okay, let's see why this is true. When we say that A is equal to B mod M, again, another way that we can write this using the division algorithm, we're saying that A is equal to, I'll say, L1M plus R, and then B is going to be equal to L2M. A different L2 of A and B aren't equal, but plus the same R. So so A is equivalent to mod B is true if and only this is true. Now, what this means, if this is true, then A minus B is equal to L1 minus L2 M. In other words, their differences are the same. Their differences are the same. Their differences are a multiple of M. Okay, now what this means, if A minus B is equal to L1 minus L2 plus M, okay, what does this tell us? Well, this is true if and only if this is true. Okay, so this is true if and only if this is true, where the L1 and R and the L2 and R are the things that you get from the division algorithm. Okay. Can you see why that's true? Think for a little bit about why that's true. Okay, so what this tells us then, if the difference of two integers is a multiple of m, that's true if and only if they're congruent mod m. So two numbers are congruent mod m if and only if their difference is a multiple of m, like we have here. Okay, so if I look at Ka minus Kb, well, Ka minus Kb, and just multiply this by K, is going to be equal to K times L1 minus L2n. Okay, so this shows that this congruence thing that we're writing equality, well, this is one of the things that sort of, there's several ingredients here, or several different things, but the equals really is an equal sign, as long as you do everything mod n. Okay, so then if our ultimate goal is to solve a congruence relation like this, we can first solve this congruence relation and then multiply the solution by b. Okay, so I want to show how we can solve a congruence relation. Solve a congruence relation like this. The best thing to do, though, is to illustrate it with an example, and I'm going to use one of the examples from the book. So let's say I want to solve 41x is equal to 1 mod 110. So let's say I want to solve 41x is equal to 1 mod 110. So what I'm going to do is I'm going to use the Euclidean algorithm to compute the GCD of 41 and 110. Now obviously our assumption here is that the GCD is always going to be equal to 1, and we can see the GCD is going to be equal to 1 because 41 is prime and 110 is not a multiple of 41. But it's not that we need to compute the GCD of A and M. We need to be able to look at the steps in the Euclidean algorithm, and the steps in the Euclidean algorithm is what's going to help us. So if you look at 41x is equal to 1 mod 110, another way of writing this, I'm going to write it down over here. Another way of writing that is to say 41x. Again, I don't know what x is equal to k times 110, and I don't know what k is, plus 1. So I kind of have an equation here, two unknowns, and I want to figure out what k or x is. Or I want to figure out. There's going to be infinitely many solutions here, and I want to figure out what they are. But I need to get at least one, and then I basically want to take the smallest one, the smallest positive one. But I got to get one solution first. Okay, but notice that I can rearrange this and write this as 41x minus 110k is equal to 1. Okay, and since, as we will see, the fact that 1 is the GCD is going to be important here. Okay, so let's use the Euclidean algorithm to compute the GCD of 41 and 110. So we're going to start off by saying we've got 110 is equal to 2 times 41. 2 times 41 is 82. So this is plus 28. Okay, and then we're going to say that 41 is equal to 1 times 28 plus 13. And then we're going to say 28 is equal to 2 times 13 plus, this is 26, plus 2. And then 13 is equal to 6 times 2 plus 1. And then as we can see, the next line is going to be 2 is equal to 2 times 1. So 1 is going to be the GCD here. Okay, now what we want to do is we want to find integers k and x so that we can kind of write 1 as a linear combination, so to speak, of 41 and 110. And notice how the Euclidean algorithm can help us do this. This first line here shows me how to write 28 as a linear combination of 110 and 41. Indeed, it tells me 28 is equal to 110 minus 2 times 41. Okay, this is good because I can come down here and 13 is equal to 41 minus 28. Now let me write the 1 explicitly. Minus 1 times 28. But I know how to write 28 as a linear combination of 110 and 41, so I can just copy and paste that here. And that'll tell me how to write 13 as a linear combination of 41. And then over here, 2 is going to be equal to 28 minus 2 times 13. This is how I write 28 as a linear combination. I'll figure out here how to write 13 as a linear combination of 41 and 110 and so on and so forth. So let me just do this a couple more times. I'll just do it, you know what, I'm just going to do it the whole way just so you can see exactly what's happening here. Okay, so 2 is equal to 28 minus 2 times 13. Okay, this is how I write 28 as a linear combination of 110 and 41. So this is 110 minus 2 times 41. And then minus 2 times 13, which is 41 minus 41. Oh, you know what? I skipped a step here. Sorry. I knew something didn't seem messy enough. So this is equal to 41 minus 28, which is 110 minus 2 times 41. Okay, so what are my coefficients on 41? Well, I've got 41 minus 2 times 41. So this is going to be 3 times 41, and then minus 110. Okay, so that's what 13 is. If I come down here and look at 2 is equal to 28 minus 2 times 13. Okay, so what do you got going on here? 28 is 110 minus 2 times 41. So this is 110 minus 2 times 41. And then it's going to be minus 2 times 13, which is what I have here. Minus 2 times 13, which is 3 times 41, minus 110. And now you can see patterns here. Like, we really just need the coefficients. Like, so we really could just kind of write this like as a vector almost and kind of work with it that way, like a vector relative to the basis of 110 and 41. Obviously, we got to be careful what we mean about that. Anyways, I'm not going to do that. But I think it might be interesting if you guys came up, you know, if you guys sort of translated it that way to see if that formalism made it a little bit less tedious. Anyways, what we're going to have here then for the 41s, we're going to have minus 2 minus 6. So that's going to be minus 8 times 41. That's going to be minus 8 times 41. And then for the 110s, we're going to have 110 minus 2. So it's going to be plus 3 times 110. Okay. So, yeah. The next one is going to be 1 is equal to 13 minus 6 times 2. Okay, again, 13 is 41. 13 is 3 times 41 minus 110. So this is 3 times 41 minus 110. And then minus 6 times 2, which is minus 8 times 41 plus 3 times 110. Okay. And so now what's going to be the 4 times 41? Well, I have 3 times 41, 6 times 8, that's 48. So 3 plus 48, that's 51. So it's going to be 51 times 41. And then for the 110, it's going to have a minus 1. 6 times 3 is 18, so that's going to be minus 19 times 41. So 1 is equal to 51 times 41 minus 19 times 41. So over here, we plug in x is equal to 41 and k is equal to 19. Okay, but at any rate, what this does is it tells us that a solution to the equation 41x is equal to 1 mod 10 is 51. Okay, so here I can put x is equal to 51. Okay, and I want to subtract. Typically, what I would want to do is I want to subtract from that answer 51. I want to subtract 110 from it as many times as I need to get the smallest positive number that's going to satisfy this. Well, obviously 51 is less than 110, so I don't need to do that. Okay, so this is again an overview for how to solve recurrences like this. Now, like I said before, if the only way that this, in general, the only way this is going to have a solution is if b is a multiple of the GCD of a and m. If the GCD of a and m is 1, then any integer is a multiple of the GCD, and so that's what we like. That's the case. Those are the cases that we're going to be looking at in this class, only when the GCD is going to be equal to 1. Okay, anyways, so that is it. That is this video. In upcoming videos, I will show how we can use these ideas and related ideas to solve systems of congruences. And this is going to be the thing that's called the Chinese remainder theorem. Okay, so it's sort of a big theorem in number theory and algebra, and it was sort of the medieval Chinese mathematician. He came up with it. I'll explain more about him a little bit later. But yeah, so I'm excited about it, and I'll probably have to wait until tomorrow to do that video, though.